Hello again, my dear students. This is the third chapter in our Introduction to Communication course offered to Year 3 after prep for Computer Engineering program. Now we will start our modulation journey, actually. Maybe for the next 6-7 weeks, we will deal with all the phases of modulation, either from an analog part or from a digital part. And as we mentioned in the previous lecture, we will start with analog communication. I believe in the previous lecture, when we make a general introduction to modulation techniques, we already have introduced, maybe from a macroscopic point of view, the main difference between analog modulation and digital modulation. However, we will come to it later on, maybe after 3 weeks from now. For the next 2 weeks, this week and the next week, we will be fully dedicated to what's called amplitude modulation, the most famous modulation and the most actually historical way of modulating sounds. So let's now start our lecture with sharing my presentations. So I can believe now that you see now my full screen presentation. And let me also start operating my laser pointer as usual. So the title for chapter number 3 is Amplitude Modulation, or what's simply abbreviated by AM. As usual, let's start with a quick scanning on the concepts of modulation in general. In the previous lecture, my dear students, we have introduced the modulation process as a 2-input process. The first input is a message, and as far as we are talking about an analog modulation technique, then the message will be an analog signal. The second input is the carrier frequency, which is analog all the way, and we actually proved that this, for the best carrier signal, is a sinusoidal signal. And the block under test, which is the modulator. Herein we have the output in the form of a modulated signal, we usually abbreviated by SFT. This is generally the overall schematic of a modulator plug. As a concept or as a function, we have studied that the main advantage or the main function of the modulator is to transfer what we call a baseband signal. Again, the baseband signal is this signal with the frequency spectrum around 0, to transfer this baseband signal into a passband signal. So whenever you have such a transfer, then you do what's called a modulation. And actually we'll go into details, and maybe you can return back to our previous lecture to understand why we do such a frequency shifting. Okay. If you remember, and we also came up that this frequency shifting is some sort of multiplication. Okay, if you remember, we consider a very important example where we have M of t, or the input is just a monotonic wave, which is a sinusoidal wave. And still the carrier is a sinusoidal. And we investigate together what will be the output. So let's now start to resolve this problem again. Okay, now you can see my very simple whiteboard. Okay, let me manage it somehow. Okay, that's perfect. Okay, let's now start. So we have M of t, which is the message, equals to AM cosine 2 pi FMT. Generally, this message may be any generic analog signal, M of t, but for the purpose of an easy mathematical analysis, we just choose it to be a monotonic sinusoidal wave. The carrier, C of t, is AC cosine 2 pi FCT. Again, please don't forget that. FM is a baseband signal, and FC is a passband signal. So logically speaking, FC is much greater than FM. And based on our understanding for the previous lecture, we say that this process is simply a multiplication process. We multiply m of t with c of t. And herein we get a signal s of t, which is simply equals to AC cosine 2 pi FCT times AM cosine 2 pi FMT. If you are somehow a concentrating student, if you return back to my previous lecture, you will find that I told you here we make some mathematical stuff here, and then we get the SFF, if you remember, and after that we plot the SFF. But I told you that we will not plot the S of t now, and we will plot it in the next section. Now it's the time to plot S of t. Okay, how can we plot this S of t? Actually, there is many methods or many ways that you can plot S of t with, but maybe the easiest way is to do that there are two time-dependent multiplied functions. You have two sinusoidal signals multiplied together. But again, don't forget that FC is much greater than F. So in a very easy way, let's do it in a form of multiplication. So we have two signals. The first signal is the m of t. Which is something like that. And the second signal is C of t, which is something like that. As you can recognize here, whenever I start to plot such a time-dependent signals, I have to have the sense that the time period here is much greater than the time period here, because simply FC is much greater than FM. Now it comes to the multiplication process. Okay, let's start thinking about the multiplication process, how we can make such a multiplication process. Okay, it's very simple. Search for zeros. What do you mean? Search for zeros. It's very simple. Whenever you have any two signals multiplied by each other, if any one of them is zero, the output will be zero. Very simple. S of t equals to m of t times c of t. So if m of t is equal to 0, s of t will be equal to 0. If c of t is equal to 0, s of t will be equal to 0. So it's very simple here. So all these points, all these points will be equal to 0. Good. Now, as you can see, all the zeros here will turn to be a zeros and s of t. But here we are multiplying with some shaped function. So, for example, here we have a constant amplitude, which is AC. This constant amplitude will be somehow shaped like that. So, for example, I will make here a dotted line this way. Okay, so I will start now to plot something like that. Okay. Then, now it comes to the first zero is m of t. So at this first zero is m of t here, you will have also a zero. Okay, so this is a zero because m of t is equals to 0 and c of t is equals to 0. Very simple like that, as you can see. Then Where is the problem? Let's continue. Okay, so what you are going to do is now, after this point, okay, this point is 0, is very logical because, as you can see, m of t is equal to 0, c of t is equal to 0, so both are equal to 0. This is very logical. So the output is 0. Now, what is after? What is after is very tricky, my dear students, because now m of t becomes negative. Then, when you multiply m of t here with this signal, which is already a negative, then you are multiplying negative with negative, then it will turn to be a positive. So you'll find something like that. Please, 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 please zoom in to this region. It's a very important point. Can you see it? This is what we call it a phase overlap. Here, what you make is that you discontinue the continuity of this sinusoidal, because in this portion you are multiplying the sinusoidal with a positive. Now you turn it to multiply by a negative, then this phase overlap starts to appear. Okay, then where is the problem? Where is the problem? Here you have to turn back to your Fourier classes. Whenever we have a discontinuity in a signal, we should expect a wider bandwidth, a wider frequency. So this is not a preferable way. This is not a preferable way to detect your message, because now you have a discontinuity, and of course this discontinuity will continue to appear whenever you have a new 0 with m of t. So this is somehow a problem with the modulation. Now you make 50% of the AM modulation. Why call it 50%? Now, your carrier amplitude is a function of time, and this function is somehow related to the message, as you can see. So this is what we call it the envelope of the carrier, because this is the envelope where you put your carrier in. So the envelope now is function in the message. If you remember, we already recognized it in our previous lecture. Maybe it's easy to be recognized here when I said, okay, I'm sorry, okay, AC, AM cosine 2 pi FCT, or simply I can write it in this way, S of t equals AC M of t, which a general M of t, any message, cosine 2 pi FCT. So now the amplitude is varying with the message. That's why it's called the amplitude modulation. However, we have the problem of this phase overlap. Okay, so how we are going to solve such a problem? We don't need to make this phase overlap. Let's ask us the question, why there is a phase overlap? Simply, there is a phase overlap because this message signal is an alternating message. What I mean by alternating message is that this message signal is alternating between the positive and negative portion. That's why it's called that's why we have a phase overlap. What if we turn this message to be a pure positive message? Then you don't have a problem. If you move this message upward so that all the message is positive, then you will not have a problem. So the solution is simply to shift the message upward back to your signal system coefficients. maybe even your circuit courses. If you remember the word DC offset, whenever we have a DC offset to a signal. So if we have this DC offset, if we shift it upward, then all the message will be in the positive portion, mathematically in the first quad, and then we will avoid such an alternating message in the plus and the minus region. Okay, then where is the solution? Let's turn back to the slides. Again, open up our pointer. So this is the example. Sorry. Okay, this is the example we just solved together with M of t is an AC, sorry, and a monotonic signal. As I mentioned, generally speaking, you can make it any analog signal. However, as we see that we have a problem. We have a problem with the amplitude modulation. This is just a reminder to our previous definitions that we have amplitude modulation, frequency modulation, and phase modulation. Here we are concerning the amplitude modulation. So now this is the message and this is the output. The output is varying with M of t, or the amplitude of the carrier is varying with M of t, as we mentioned. So what we are going to suggest is this plot. Okay, what is this? Or what is the difference between this and that? Here, we still have the mixer and we still have the carrier. Perfect. So this part of the block is common. You have the mixer and the carrier. But here you do two more steps, actually, my dear student. First, you multiply the message by some unknown k. We will call it later on the modulation index or something like that. So please forget it for now. So we just multiply this M of t by constant, and then we add 1. But here, you directly multiply the message with the carrier. So this is the output. Now, let's write an equation to express this S of t. Okay, let's see it. Let's stop sharing it and go to our simple whiteboard. Now this is the new model. Now this is simply the new model. We have the message, M of t. And then we have a multiplication with a constant called k. I'm not so good here. I'm sorry, I lose my concentration for a while. So we have the message, M of t. And then this message is multiplied by gain unit. And then we have an adder with a 1 as a DC constant value. After that, we have our mixer with the C of t. And then we have this S of t. So this is simply the modified block. Let's now start to examine the mathematics of this modified block. So let's do it. Now we have this constant called k. So after this, at this point, at this stage, the message becomes to be k times M of t. As you can see. So here, one more step here. You add too hard to be open, but then it's too hard to be open. Okay, no problem. We have another one. Okay, so now we have at this stage it is 1 plus k M of t. So now the two input of the mixers are C of t and 1 plus k M of t. So simply speaking, you can write down a general expression for S of t. S of t is equals to 1 plus k M of t C of t. Of course, you know C of t, it's an assigned unit, so you can make it AC 1 plus k m of t cosine 2 pi fct. This is a general expression for s of t for any m of t. Perfect. Then, does this schematic solve our phase overlapping problems? Let's see. Okay, let's do it. In order to check it, let's turn back to our original example. The example we considered in the beginning of the lecture, which is a monotonic modulated signal. We have a single tone sinusoidal. So we are going to apply this schematic on our example, where we have m of t is am cosine 2 pi fmt. Very simple. So what you are going to do now, very simply, my dear student, is that you are going to substitute this m of t over the general equation for s of t. And then we check, does this schematic solve the phase overlapping problem or not? Okay. Mathematically, it's very easy. So s of t equals AC 1 plus k, this hidden unknown, am cosine 2 pi fmt cosine 2 pi fct. This is your new s of t. This is your new modulation factor. So, what you are going to do now, let's start to plot this signal, because in the first example, we detect this phase overlap. If you remember, my dear student, we detect this phase overlap. Whenever we plot this signal, we find that the message is alternating from positive and negative, and that's why we have this phase overlap problem. So now we are going to repeat it by just doing the same message. We are going to try to plot this message or this signal. Now it's not, life is not that easy, because before, yeah, the carry is the same. It's AC cosine 2 pi fct. So we have a constant carry, and all the time you will have a constant carry. Now you have a new form of a message. It's 1 plus k unknown am cosine 2 pi fct. Okay, that's perfect. Let's start with investigating the message first, or this, what is inside the bracket. Let's start first to investigate what is this, how we can plot it, for example. So first, let's start with m of t. M of t is a very simply is a normal message, am cosine 2 pi fmt. You multiply by k. Okay, so k is a constant. If k is greater than 1, then the message will magnify. If the k is smaller than 1, the message will be attenuate. So just a dummy for now, it's just a dummy variable. So we can simply say, okay, something like that. And what is only different is that now this amplitude is called KAM instead of EM. That's all. This is the only difference. Then you add 1. Here you have to stop. Okay. Adding 1 is simply shifting this signal upward. Again, adding 1 is simply shifting this signal upward. Why? Let's make it with a very simple example. If I told you that this is 5 and this is negative 5, and I add 1, then 5 will become 6 and negative 5 will become negative 4. Very simple. You should just shift it upward. But am I able to know the amount of shift? I don't know K and AM. So this shift may turn the message to be like that. Or the shift may be to turn the message to be like that. Or it may be like that. All these three versions are shifted version of this message. But it simply depends on the amount of the DC shift, of the offset shift, with respect to this bottom negative value, which is negative KA, negative KAM. This is very simple like that. So if 1 is greater than negative KAM, then the 1 will shift it totally to this version. If 1 is smaller than KAM, then you will have part of the signal positive and another part of the signal negative. If 1 equals to KAM, then it will be typically on the x-axis. Very simple. Let's take an example. If, forget this, so if this is 0.5 and negative 0.5 after multiplying with k. So simply, when you add 1, it turns to be 1.5 and 0.5. 1 plus 0.5 is 0.5, and 1 minus 0.5 is 0.5. So 1.5 and 0.5. But if it is 1 and negative 1, then 1 plus 1 will turn to be 2, and 1 minus 1 will turn to be 0. If it is 3 and negative 3, then it will become 4 and negative 2. So the amount of shift is depending on the new value KAM. Or in other words, it depends on K, because you can never know AM. AM is a message. It depends on the user. But what is controllable from your side is simply the K. The K is what's controllable. So please don't forget which one from these graphs you are seeking for. You told me that. This is an acceptable graph. Sorry, this is an acceptable graph because it's all in the positive sign. Again, the problem where when the message alternate from positive and negative, if you remember. So I am seeking now to push the message upward to make it all in positive. So in the first version, it's okay. The message is all in the positive. Now this is not okay because you still have a portion in negative. Here, it's okay because you have a version of positive. So what you are seeking for is to make K in a condition either to give you this state or this state. You can make it yes because K is a controllable parameter, so you can control the K whenever you want. Maybe a few months ago, and we can now find an exact relation for K. So if I assume, for example, that I am in this stage, for example, this stage, then it's become very easy. So what you are going to do is as follows. First, you are going to plot 1 plus K M of t, which is something like that. You have your carrier. Of course, my plotting is too bad because sinusoidal should have a fixed frequency. I'm not plotting a fixed frequency, but assume it's fixed, please. So this is a carrier. Now you are doing multiplication. Very simple. Here you have a constant amplitude, which is AC and negative AC. Now you multiply this constant amplitude by this signal. So it becomes like that. In a very easy and simple manner. Okay, so now this is your new envelope, and now you can plot your message, or sorry, your carrier. in this way. Now this is a carrier, and your message is hidden in the envelope of the carrier. So this is your message, hidden in the envelope of the carrier. Your new amplitude, your new carrier amplitude is very simple. It's an AC, 1 plus K AM, this manner. Hello? Hello? Evan. طب تديني مثلا تلت ساعه عشان بسجل محاضره اخلصها ولا ممكن؟ اوكي ميرسي شكرا. So now this is your carrier and this is your message, your envelope of the carrier. So it's very easy, as you can see, in a very direct way. Now, we know this expression, and we can investigate more in this expression. How? Let's start thinking about the maximum and the minimum of this expression. The maximum and the minimum of this way. So, I will keep this slide, slide number 4. So I will keep this slide to show it from time to time because we will need it. So let's rewrite the expression again. S of t equals AC 1 plus K AM cosine 2 pi FMT times cosine 2 pi FCT. This is our expression. Okay. Okay, what you are going to do is simply, I'm searching for, okay, I'm searching for the maximum and the minimum. The maximum will occur. Again, please remember that this maximum and this minimum are depending on the message, not on the carrier. So the maximum will occur when the message is maximum, and the minimum will occur when the message is minimum. Okay, let's return back. As far as we are seeking to recognize the amplitude, so the amplitude of this carrier is this equation. The main variable of this equation is this cosine function. This cosine function has two conditions. If the cosine function is equals to 1, so this is the maximum. If this cosine function is equals to 0, then is equals to -1. I'm sorry. This will be the mean. Any cosine fluctuate from -1 to 1. So the question is, am I interested in the maximum or the minimum? Let's see. The problem of the phase overlapping is actually related to the minimum. Please remember. Please remember this slide. Here, when the minimum becomes negative, the phase overlapping starts to appear. That's why we have phase overlapping. So, what you are targeting to is to avoid this minimum to be less than 0. Your minimum value should be 0, not less than 0. So you can write a very important equation and say, okay, the minimum of S of t is equals to AC 1 minus, because now cosine will be -1, 1 minus K AM this should be greater than or equal 0. Very important condition. Now, what if we go to the minimum? So AC 1 minus K AM is equals to 0. What if we have such a condition? This will lead to the minimum value for your signal. So if you go to this condition, you will have what we can call a fair modulation. So your minimum will turn to be typically equals to 0. Okay, so this is a very important, my dear students. This is somehow one of our critical points when we are doing modulation, because whenever you have a K that leads that this term will be greater than 0, we will call this over modulation and under modulation, as we will going to see now in our slide. So let's turn back to the slides and let's open our pointer. Now this is a new modified system where we have this modulation index, the added value 1, the carrier, the mixer, and the modulated output. And this is the new form of the modulated output. It's AC1 plus K M of t cosine omega c t or 2 pi of 6. Okay. So what if you have M of t as a monotonic wave? This is typically the same example we just did together now. Herein, we write it in somehow in a different manner, where we insert the AC inside the bracket instead of 1 plus AC. So we make the DC shift is equals to AC. So we put here an AC. So when you have an AC common factor, you get this K, where K is equals to AM over AC. Mathematically, both will end to the same base. And here we define K as AM over AC. However, this is will not different some. But what is interesting is this. If you make this modulation factor is equals to 1. What I mean to make this modulation factor is equals to 1, let me return again to avoid any confusion. This is the modulation factor. This is K. If you put this is equal 1, this is typically what you need. 1 minus 1 is equal 0. So this is typically what you need. To put the modulation factor is equals to 1. So you will reach the minimum state. So simply, what you are going to do is as follows. Again, we open our here. So this is what's called a modulation index is equals to 1. So you have, again, as you can see, the minimum touches the x-axis. So this is the first case. What if it's 0.5? Then you have what's called a modulation 0.05. So you have what's called an under modulation. So you shift your signal in a very high manner. So as you can see, this now your signal is up and down, and then you have this case. And what is called the over modulation, when you have, if you remember, this is our first case. This is our first case when we make this phase overlapping. So you can see it here and there. This phase overlapping problem when you have K or the modulation index is greater than 1. So these are the three main conditions. So these are the three main conditions. Of course, the overmodulation is unwanted modulation because it has this discontinuity in the carrier, and also it has a problem with the frequency spectrum. We always tend to have what we call it either an undermodulated signal or an fair modulated signal. Maybe later on in our tutorial, and maybe in the next part of this, in the next parts of this lecture, we will investigate more the difference in the term of management, power management, I mean, between the undermodulated modulated and overmodulated. Finally, this is our output. We have our signal in this way, as you can see, AC 1 plus K M of T, and this is our raw signal, and this is our carrier, as you can see, and this is our, of course, here we have an undermodulated signal because simply the minimum of the signal is still greater than 0. So this is our signal. Again, in another way, sometimes we call this the modulation, but it's just a different terminology. Here, I believe you already know this. This is the maximum of the signal, and this is the minimum of the signal. I believe we already investigated these two conditions when we have AC 1 plus K M of T here, and when we have AC 1 minus K M of T there. So this is the minimum, and this is the maximum, and we call this the modulation depth. Finally, if we would like to plot the spectrum, I believe we already did this in our previous lecture when we plot the frequency spectrum. We say that whenever you have a message here, then you will have what's called a carrier and two messages. But now, please take care. So let's now return back to our whiteboard. Now the new expression is as follows: is AC 1 plus K M of T cosine 2 pi FCT. This is the new expression. Okay. Then, if you have any message signal, this is M of F. Now, what you are going to is you are multiplying this message with a carrier. So simply, you will have at FC and at negative FC, this shifted message. Okay, this is actually the modulation process, as we already understand that. But what about this one? If you just multiply this one with what's outside the bracket, you will know that this is a carrier. So now you are sending two different messages. You are sending the message multiplied by the carrier, okay, and you are sending the carrier alone in this one. So you will have something like that. This is a carrier. Okay. This is very important, my dear students, for our next parts. Because in our next parts, we will investigate different types of AM modulation. Here, as you can see, I'm sending the message in addition to the carrier. And let's have a look for a few seconds. And let's return back to my question in the previous lecture. When I told you about this portion of the message, whenever we start our lectures, I told you a fact that no physical meaning for a negative frequency. And Fourier used the negative frequency just for mathematical description to make his function as an even symmetric function around the y-axis. However, when you shift the frequency, when you set this baseband signal to a passband signal, this negative frequency region also has been shifted. So, what does it mean? Again, let's turn back to the theory of Fourier. Fourier told us, yeah, don't worry, the physical meaning is here, and this is just an error. That's right. So the physical contents are here, are from 0 to P, for example. So this is a physical content, and this is just a mirror to the physical content. It is just like you are standing in front of a mirror. You are one person, but you have two images. Your real one and the mirror image. Now, when we shift it here, we have two types of the signals: the original signal and the mirror signal. That's why we call this AM modulation as double sideband AM modulation? Because you are sending both sides of the message, the positive side and the negative side. We call it a double sideband. So in this way of modulation, you are sending a double-sided message in addition to the carrier. So maybe later on in the next lectures, or sorry, in the next parts, I will tell you, okay, I will send these two ports, but I will not send the message. And what about the phase overlapping? I will solve it by way or another. Let's see. So we will call it a double sideband suppressed carrier. I suppress, I neglect, I reject, I kick out the carrier. So this is a second message, a second technique. So the first technique is simply to send both sides of the message, the double-sided message, in addition to the carrier. The second technique is to send the message without the carrier. Do we have a third technique? Yes. Single side band. To send only one side, because you will say, okay, this is a redundancy. This merit is just a redundancy. I can send only one message or one side. So I will kick out also the redundant part of the message, which is this negative part, and I will kick it out, and simply I will send only a single message. So this is the short type. We also have a fourth type, which is called a vestigial sideband. I believe we will not investigate in it, but let's know the word is a vestigial sideband. So, but it's maybe out of focus. Maybe your colleagues in electronics and communication can investigate more about it. So this is generally the main four types of AM. I will come again to this types later on in the next course, but let's have now our own overall view. So simply by returning back to the slide, that's why I call this slide a double-sided AM. It's a double-sided because now, as you can see here in my presentation, I have the positive side, or the positive side, yes, and the negative side, and the carrier. That's why we have a double-sided AM. Okay, that's perfect. So in the next lecture, or I'm sorry, the next part, I'm going to investigate more about the demodulation. Simply, if the modulation is the transformation from the baseband signal to a passband signal, the demodulation is simply the returning back from the baseband signal, sorry, the passband signal to a baseband signal. So now you have the signal over the carrier, and you return to, and you are seeking for returning it back to that baseband format, to the original format. So this will be the topic for the next part. Thank you, my dear students, for your concentration, and I will be willing to see you again in part number 2 of the amplitude modulation.